So we looked last day at parallel plate force problems. Today, parallel plate energy problems. And in fact, in the homework that I went over, Nicole and Mitchell, that equation is going to be showing up an awful lot. We're going to often end up with QV equals a half mv squared. So, a couple of reminders. For parallel plates, this lovely little setup here, the voltage is given by the battery. You want more volts, hook up a different size battery. And it varies directly with the distance between the plates. And recall that for a test charge placed at a point whose voltage is known, we can find the potential energy by going QV. Example 1 says, okay, find the work done by an external agent, little invisible angels, let's say, that move a positive 2 microcoulomb from the negative to the positive. Now, which way does this positive charge want to fall, up or down? Down, because this is more negative than that. So you would need an external agent, invisible angels, lifting it up, working. They're adding energy, they're lifting it. In fact, when they let it go, it's going to want to come crashing back down. How much work? Well, work equals change in potential plus change in kinetic. Oh, Andrew, what does it say in brackets? And I know you're going to be a bit lost because you've been, but watch the videos. But for now, what does it say in brackets? Assume what? So what can you tell me about the change in kinetic? Yeah. Okay. By the way, you'll notice I stayed away from force times distance. I think force times distance would work in this case because the force is constant, because the electric field is constant. Oh, but Zay, we noticed when you asked me and I did it the forces way, was it more lines and more work? Oh, well, heck, let's go energy then. What's the change in anything? Final minus initial. How much potential energy does it have right here? And I'll put it in gravity terms, on the ground. Brianna. Yeah. And in fact, I can now simplify this to, oh, here's our equation that has both voltage, a charge that we're moving, and potential energy. We can say that potential energy is equal to Q times the change in voltage. Although, Matt, because voltage is almost always a change in, we'll often get sloppy and stop writing the change in, just like we did for time a long time ago. Yeah, time's always a change in. QV. All right. Q, 2.5 times 10 to the negative 6, the microcoulombs. V, 120 volts. How much energy will this charge gain? How much work will this mysterious external agent have to do? (3.6 times 10 to the negative 4? Double check me. No? 3.0? Yes, 3.0, not 3.6. 3.0 times 10 to the negative 4? Units? Work? Joules? You okay there, Nicole? Because I'll stop the car and make you get off, so help me. Okay. Example 2. Now what we're going to do is, instead of having it not want to move, we're going to repel it. So this is an electron, negatively charged. This is negatively charged. Emily, which way is this electron going to want to go? Can you give it out loud as a direction instead of pointing? To the right. And we're going to get clever. We're going to cut a very, very small slit, put a little hole right there, so the electron can actually go shooting through the hole like an electron gun. Very easy to do. Oh, How fast will it be traveling? It says there is no external agent, so system energy is conserved. Oh, energy is conserved? This was like a job for kinetic energy initial, potential energy initial, equals kinetic energy final, plus potential energy final. Are any of these 0? Are we starting at rest? I think so. And we're going to fall. Now, here's where the gravity analogy sort of breaks down. Brett, we're going to imagine that we're falling, this is the ground, and I guess we're falling into a hole in the ground, except somehow we're not going to keep speeding up once we get to the hole in the ground. What I'm saying here, Matt, is I think my final potential energy is 0. All of my initial potential is going to become kinetic. This electron speed is going to come from the fact that it's going to travel through a repulsing voltage, a repelling voltage. Trevor, we just said that potential energy is Q V initial, and kinetic is a half M V final squared. And Nicole, here's the equation that you asked me about earlier, again. Katie, what do you want me to find? How would I get it by itself then? How would I get this by? How about times by 2, because that way no decimal, and divide by, and then how I get rid of squared? In fact, we get kind of a nice little equation. I guess for an electron gun, the final, for any charged particle gun, the final speed is going to be 2 times the charge times the voltage you send it through, divided by the mass, square rooted. That's going to be a equation that pops up fairly frequently. Final speed is going to be 2. Did they tell me the charge on the oh, electron. They don't need to tell me the charge. What's the charge on an electron? 1.6 times 10 to the negative 19, right from your formula sheet, the elementary charge. How many volts are we traveling through? 125 divided by mass. Oh, mass of an electron. That's on your formula sheet. I know it's 9.11, but I can never remember the times 10 to the... Trevor, what'd you get? What is it? Okay. Okay. What's the answer? It'll be fast, like 10 to the 6th or 10 to the 7th, probably. Maybe 10 to the 5th, but it'll be fast. You get 6.63 times 10 to the 1, 2, 3, 4, 5, 6. Okay. So, as we see in the above calculation, when a particle is accelerated from rest, simplest case, by a voltage, we have a simple energy equation. Potential energy equals kinetic. In fact, we get QV equals a half mv squared. Except, as we wrote here, we must take care in this equation not to confuse V with V. So my high school, actually my college physics teacher, he always taught us put little wings on your capital V, and that way it stands out. Example 3. An electron already moving at 5 times 10 to the 5th meters per second. Oh, now we're not starting out from rest. Enters a set of accelerating plates. Find its speed when it leaves the plates. John, what does this want me to find in example 3? Did they say velocity or speed? Let's try a scalar approach. You know what? I think I might try conservation of energy. Kinetic energy initial plus potential energy initial equals kinetic energy final plus potential energy final. Are any of these zero? Now, last time we said we're starting from rest and we did this. This time, sadly, we can't. Okay. But you know what? I think once I travel through all of the voltage, I've used up all of my potential energy. I'm going as fast as I'm going to go. We're going to get a half mv initial squared plus mgh initial equals a half mv final squared. Oh, wait a minute, Mr. Dueck. This isn't potential energy anymore. mgh. That's gravity, Mr. Dueck. Don't be silly. What am I going to use, Nicole? Yes. Mr. Dueck, did you do it on purpose? Yeah. Do I know M? Oh, it's an electron that's on my sheet. Yes, yes, yes. Do I know V initial? Yeah, they told me. Do I know Q? It's an electron. 1.6 times 10 to the negative 19. Do I know the voltage that we're traveling through? Yeah. Oh, I can find V final. I think I'm not going to try and get the V by itself. I'm going to crunch the left side, get a number, and then move the 1/2 and the M over and square root. Otherwise, this is a bit yucky. So we're going to get 0.5 times 9.11 times 10 to the negative 31 times 5 times 10 to the 5th squared plus 1.6 times 10 to the negative 19 times, oh, what is the voltage that we're traveling through? Don't say 600 because it's not. Look carefully at the diagram. How many volts are we traveling through? 500. Yes, that's the change in voltage. And that's why, Matt, I said voltage is always a change, but we just stopped writing the delta. Yeah, I want 500 volts. This equals a half mv final squared. What was that? Right? Who was asking? Matt was? Oh, jeez. About 5.5, Mr. Dueck. 5 times, geez, times 10 to the 5th squared plus 1.6 times 10 to the negative 19 times 500. So I get 8.001385 equals a half mv squared. So V final squared is going to be, what did I say it was? 8.0114 times 10 to the negative 17 divided by a half, or I could have times by 2, Katie, and divided by 9.11 times 10 to the negative 31, square rooted. And I can get rid of the squared, Mr. Dueck. So this number times by 2 divided by 9.11 times 10 to the negative 31, square root, and I get 1, 2, 3, 4, 5, 6, 7, 1.33 times 10 to the 7th. moving fast, but I'm not going faster than light, so this is still legal. And this is going to lead us into how old televisions used to work. Which televisions? The kind that when you looked at them from the side view, you had the screen, and then the back end kind of jutted out like that, like an old computer monitor. This is how TVs worked for about 50 years. And they were actually a very simple process. They used something called a CRT. A CRT is a cathode ray tube. Okay? And here's what we do. Don't write this next bit down, it's going to be messy. We build an electron gun, and the way we build an electron gun is we just have a coil of wires and we send a current through it. And we also have a set of negatively charged plates right there and a set of negatively charged plates right there, and we send enough current through here that electrons get repelled from here. So when an electron gets repelled, it might start to travel this way, but when it starts to travel this way, it's going to get repelled. In fact, very quickly, it's going to get pushed to the middle. We have a very small slit right there, so only electrons that travel fairly straight can make it out through this small slit. And you get, essentially, an electron gun. Mitchell, they're coming out almost bang straight. Not quite. Why would you want to do that, Mr. Dueck? Oh, watch. So here's our electron gun. We have some plates that accelerate it. So this is negatively charged right here. This might be positively charged right here to pull it to the right. But we put a small slit right there. So the electron comes shooting through here, starts to slow down a little bit because now this is attracting. Who cares? It's got enough speed, Andrew, to keep going. And we have some deflecting plates. If we charge the top positive and the bottom negative, which way will this electron get tugged as it goes through here, up or down? In fact, it'll get deflected maybe to about there. What if I bump up the voltage? Will it get deflected more or less? More. What if I lower the voltage? Will it get deflected more or less? So I can put it anywhere I want to by changing the voltage. Or, Emily, if I reverse the voltage and make this positive, heck, I can put it down there. With me so far? Okay. Then what we do is we take the inside of the television screen and we paint it with a phosphorescent paint. A paint that will glow, bing, when it gets hit by an electron. That's a television. Really? Yeah. All we do then is we hook this electric source, this electron gun, and this voltage. We hook it up to the TV image that's being broadcast so that the voltage is directly proportional to the image. And what happens is one electron gets sent right there, another one gets sent right there, another one gets sent right there, another one gets sent right there. But when you're on the other side looking, you don't see a bunch of little dots hitting like raindrops. They're hitting so fast, your eye translates it into a single image. And it refreshes that image every 60 seconds. Sorry, 60 times every second. 60 hertz. Okay? In the simplest cathode ray tube, a beam of electrons is accelerated by one set of plates, deflected by another, hits a fluorescent screen which glows. So it says, describe the motion of an electron beam in a cathode ray tube. Works like this. Works like this. Now for color, that's for black and white TV. For color TV, they have 3 different electron guns and they have 3 different types of paint. One will fluoresce red, one will fluoresce blue, and one will fluoresce green, and your eyes blend the colors. This is not, Sean, how a flat screen works. We'll look at how a flat screen works in a second. Okay. Example 5 says, A, find the speed of the electron beam after the electron gun. Okay. What's our initial speed? 0. You know what? We can go straight to saying all of your potential is going to become kinetic. in this section right here. In fact, we can jump straight to saying the speed that the electron leaves the accelerating plates, the electron gun, at is going to be the square root of, what was it? 2q voltage over mass. Two times 1.6 times 10 to the negative 19. How many volts is it being accelerated by? Connor. How many volts is it being accelerated by? Yep. Divided by, oh, mass, electron. Connor, what's the mass of an electron? You got your sheet there? 9.11 times 10 to the what? Yeah. Negative? Yeah. How fast will this electron be traveling when it leaves the gun and starts heading for the back of the TV screen? Matt, what'd you get? Did you square root? Because you're faster than light. If you're saying, because light is times 10 to the 8th, then nothing goes faster than 3 times 10 to the 8th. Matt, what'd you get? Anybody else? 2 point what? 2.05 times 10 to the what, Katie? 7th or 6th? 7th? Okay, they come shooting out there. Well, of course they come fast. Your eyes can't even see them moving. They're moving so fast. So look up. The electron does this. And then it hits this section. Right when it gets here, which way will it start to feel a force? Which way will it start to feel an electric field? Which way will it start to want to move, up or down? Up. It's going to get deflected. So B says, find the vertical acceleration. Well, there's going to be a force, F equals ma. We're going to ignore gravity because, Sean, an electron is so light. Yeah, okay, then forget it. We're not going to worry about mg. Oh, and it's an electric force that's deflecting it, so it's Fe equals ma. Which electric force? Well, I can't use KQ1, Q2 over R squared. It's not 2 point charges. You know what my electric force is going to be? QE. Where E is the electric field. Oh. Which electric field? Am I going to use this one here? The one with the R squared? No, because that's for a point charge. I'm going to use the electric field for a voltage. Change in voltage over distance. Q voltage over distance equals ma. I think the acceleration is going to be QV over md. Q 1.6 times 10 to the negative 19. V, which voltage am I going to use here? The deflecting voltage. How big is the deflecting voltage? Look at your diagram. How big is the deflecting voltage? 750. All divided by 9.11 times 10 to the negative 31. And the distance that it can be deflected, that it's traveling for, is, not the horizontal distance, the vertical distance, that's part of the force, 0.02. Matt, what do you get? Brett, what did you get? Still writing. Okay. .59 times 10 to 32. That seems maybe not. Anybody else? Yeah, 6.59 times 10 to the 32. 13. I'm sorry. That sounds better. 6.59 times 10 to the 13th. Yes? No? To the 15th. Did you go centimeters or meters? 0.0. Okay. So sorry, what was it, Katie? Units, acceleration. Which way is it going to get accelerated? Look at your diagram. Up or down? Jacob. In fact, you know what? Let's call this AY for vertical acceleration. What's your horizontal acceleration? Nothing. Nothing. So right now we have two speeds, Brett. This is almost like a projectile in that we have a horizontal speed right here, which is constant, but vertically it's going to start to accelerate. C. Mitchell, what does C want me to find? Time to travel from here to here. In fact, the time to travel 5 centimeters. Okay? T equals, well, let's start out like this. Distance equals velocity times time, not plus a half at squared, because horizontally there is no a. Which means that the time it's going to be between the plates for is distance divided by velocity. How long are the plates? 5 centimeters, 0.05. What's the velocity? 2.05 times 10 to the 7th. It's not between these plates for very long. For how long? .44 times 10 to the -9. But here's the key. For those 2.44 times 10 to the -9 seconds, it is accelerating upwards as well. In fact, what it's doing is this. Kind of curving. We're going to ignore the curve. We're just going to treat it as roughly a straight line. Because D says, find the angle and the speed at which it leaves. Well, here's my argument for D. It traveled 0.05 centimeters this way. How far will it travel vertically? While it's between the plates, how much will it get deflected by? Well, what's its vertical velocity when it hits these plates? Careful. What's its vertical velocity when it hits these plates? Has it started moving up or down at all yet? No. So what's its vertical velocity initial? Kara. 0. Oh, and what did we say its vertical acceleration was? 6.59 times 10 to the 15th. And we know time, we just figured out, was 2.44 times 10 to the negative 19. Could you find how far it's deflected vertically? Well, it's going to be VIT plus a half AT squared. Oh, hey, VI was 0. Yo. 19, thank you. I got 19 from the charge. Thank you, Kara. Kara? Kayla? Wow. Apparently my names are wrong, too. You know what? I think I can go like this, then. A half times the acceleration, which was 6.59 times 10 to the 15th, times the time, 2.44 times 10 to the negative 9 squared. It gets deflected by almost 2 centimeters. The 5 centimeters it's traveling sideways, it gets bumped by 1.96 centimeters. .0196. Is that okay, Connor? You able to visualize this, right? It's going through there and gets deflected. What did part D want me to find? Angle, did you say? I think that's my angle. Which trig function? Which trig function? Tan, and make sure you're in degrees, Math 12 students. Yes? I think theta is going to be the inverse tan of 0.0196 over 0.05. Mode. Degrees. Inverse tan of 0.0196 over 0.05. You know what? The left deflection angle is 21 degrees. Could I find the final velocity? Well, I would have to, I know Vx. Vx is 2.05 times 10 to the 7th. Now that I know A and D, I could probably find Vy final. I could add those tip to tail. We're going to stop here. But we can do an awful lot. This is how a TV works. How does a TV work? Like this. Continue. So what's your homework? Number 1. Number 2. Number 3. 4 is good. 5 is good. Skip 6. 7 is good. 12. Yeah, we'll pause there. There's lots of extra questions as well. And then I got one more video to show you.